We'll start in 1 minute. In a few minutes, we'll start section 7.8 on improper integrals. But first, we'll do a few more things from section 7 on approximate integration. On Wednesday, we applied the trapezoidal rule and the Simpson's rule with n equals 4 to approximate this definite integral of 1 over x squared dx from 1 to 5. And I did the arithmetic. The trapezoidal rule with n equals 4 gives us an approximation of 0.9436 and 1 repeating. Simpson's rule gives us an approximation of 0.837 and then 407 repeating. And we can compute the actual value of this this definite integral, and it turns out to be 0.8. So comparing the trapezoidal rule with the Simpson's rule, it looks like the Simpson's rule is quite a bit closer than the trapezoidal rule. We also looked at the error estimates for the trapezoidal rule, the midpoint rule, and the Simpson's rule. So these are the formulas for calculating how exact an approximation will be for a given value of n. Okay, so we'll put a couple of those error estimates to use. Okay, so referring back to the page that we started with, we used the trapezoidal rule and the Simpson's rule to estimate this definite integral with n equals 4. And from the other page, the trapezoidal rule gave us an estimate of 0.9436, where the 1 repeats forever afterwards. And then the Simpson's rule with n equals 4 gave us an estimate of 0.837, with 407 repeating forever, and the actual exact value of that definite integral is 0.8. Okay, so we're going to compute the error estimates for the trapezoidal and Simpson's rule. So for this function, or the integrand, the function in the integrand is 1 over x squared. So f of x is 1 over x squared, which we can think of as x to the negative 2. For the trapezoidal error estimate, we need to know what the second derivative of f is. And for Simpson's rule, we need to know what the fourth derivative is. So we'll go ahead and compute those derivatives now. One way to denote the first derivative is putting 1 in parentheses up here. This is the first derivative of f, which is negative 2 times x to the negative 3. The second derivative of f with respect to x is positive 6 x to the negative 4. The third derivative is negative 24 times x to the negative 5. And then finally, the fourth derivative is 120 times x to the negative 6. Okay, so the error estimate for the trapezoidal rule, I'll jot that down here. It's given to be less than or equal to k times b minus a to the third over 12n to the second. And k for the trapezoidal rule is the largest value that the second derivative of f can be on the interval from 1 to 5. Well, the second derivative is 6 times x to the negative 4, or 6 over x to the 4th. And on the interval from 1 to 5, the largest that this could be is when x is 1. The smallest it can be is when x is 5. So the second derivative will be less than or equal to 6. For all values of x on that interval. So this is our k value for our error estimate. B minus a is just 5 minus 1. So b minus a is 5 minus 1, or 4. Our value of n is also 4. And so the error estimate, when we put in those numbers for the trapezoidal rule, when n equals 4, less than or equal to 6 times 4 to the third, divided by 12 times 4 to the second. And when we do the arithmetic, we get 2. So our estimate for the trapezoidal rule is definitely within 2 units of 0.8. So this looks like a very conservative estimate. So this is telling us, once again, when we use the trapezoidal rule for n equals 4, we're going to get an estimate that is within 2 of the actual value. Okay, now let's compute the error estimate for the Simpson's rule. So I'll write down what the Simpson's rule is here. This one is k times b minus a to the 5th over 180 times n to the 4th. And this value of k for the Simpson's rule is the magnitude of the largest possible value of the 4th derivative of f. So less than or equal to k. Okay, so the 4th derivative, fourth derivative is 120 times x to the negative 6, or 120 over x to the 6th. And so on the interval from 1 to 5, what's the largest possible value of 120 over x to the 6th? Yeah, 120. When x is 1, this is the largest that it can be. For other values, they get smaller. So 120 is our value of k for this one. Okay, so we can compute the error estimate for the Simpson's rule. So k is 120, b minus a is 4 again, 4 to the 5th, divided by 180. N is 4, so 4 to the 4th. And we get 2/3 times 4, or 8/3, which is 2 2/3. And our Simpson's approximation is much closer than 2 2/3. It's less than 0.4 off. So this looks like a pretty conservative estimate. Yeah, on the next page, we want to find how large n has to be to guarantee that the trapezoidal rule approximation of the definite integral of e to the x squared from 0 to 1 dx is accurate to within 0.00001. So this number is 1/100,000. Yeah, tenths, hundredths, thousandths, 10 thousandths, 100 thousandths. So 1/100,000th. So just as an aside, this decimal number is equal to the fraction 1/100,000. Yeah, 1/100,000. Okay, so our f of x is e to the x squared. And for the trapezoidal rule, we need to know what the second derivative is. So the first derivative, using the chain rule, is 2x times e to the x squared. And then the second derivative, first we use the product rule, and then, so the derivative of 2x with respect to x is 2 times e to the x to the second, and then plus 2x times the derivative of e to the x squared, which is 2x e to the x squared. So we'll simplify this a little bit. If we factor out e to the x squared, then inside the parentheses we have 2 plus 4x squared. Okay. So all of the values of the second derivative are positive on the interval from 0 to 1. So we don't really need the absolute value symbols, but I'll go ahead and put the absolute value of the second derivative of f of x has to be less than or equal to k for all values of x on the interval from 0 to 1. So we want to find the maximum possible value of the second derivative on the interval from 0 to 1. So we can tell pretty much by looking that the second derivative is an increasing function on that interval from 0 to 1. So the largest possible value will occur when x equals 1. So when x is 1, we get e to the 1 squared, or e, times 2 plus 4 times 1 squared, which is just 2 plus 4, or 6. So 6 times the number e is our k value. Okay, so our error estimate for the Simpson's rule, I'll write down the formula again, less than or equal to k times b minus a to the 5th over 180 n to the 4th. So our value of k is 6 times e. B minus a is just 1 minus 0. And then 1 to the 5th is just 1. And then divided by 180. Oh, we're not doing the Simpson's rule. Sorry, we're doing trapezoidal rule. Yeah, someone online straightened me out. Yeah, we want the trapezoidal rule. So the trapezoidal rule is k times b minus a to the 3rd over 12n to the 2nd. So our value of k is still the same because it's the second derivative for the trapezoidal rule. So 6 times e. B minus a is 1. 1 to the 3rd is 1. So 6e is in the numerator, and 12n to the 2nd is in the denominator. And we want our error to be within 1/100,000th. You can write the decimal number or the fraction. Either way is okay. And then we solve this inequality for n, and that will determine how large n has to be in order to get an approximation that's within 1/100,000th. We can simplify the left-hand side a little bit. 6 divided by 12 is 2. So we get e over 2n to the second is less than or equal to 1 over 100,000. And if we multiply both sides by 100,000 and also multiply both sides by n to the second, we'll get 100,000 times e over 2 is less than or equal to n to the second. And we can simplify the left-hand side a little bit. 100,000 divided by 2 is 50,000. So the left-hand side is 50,000 times e less than or equal to n to the second. So I was going to bring a high-powered calculator, and I didn't. But if you compute the square root of 50,000 times e, I do remember that n is more than 300. I don't remember the more precise answer. But when you get a decimal number, then just pick n to be the next larger integer, and that will guarantee that the trapezoidal rule will give you an approximation within 100,000. It's over 300 for n, so how would you like to do that by hand? It's bad enough when we use n equals 4. So n 300 and something is something that you would want to program a computer to do, probably. Okay, now we'll move on to the next section, 7.8. On improper integrals. So improper integrals come in different forms, different types. Okay, type 1, improper integrals of type 1. So we have 3 parts, A, B, and C. Suppose a function f of x is defined on the interval from a to infinity, such that the definite integral of f of x from a to t exists for every real number t greater than or equal to a. Then we say that the value of this improper integral from a to infinity of f of x dx is equal to the limit of the definite integral of f of x dx from a to t as t approaches infinity, provided that the limit exists. Okay, in part B, suppose a function f of x is defined on the interval from negative infinity to b such that the definite integral of f of x dx from t to b exists for every real number t less than or equal to b. Then the improper integral of f of x dx from negative infinity to b is equal to the limit as t approaches negative infinity of the definite integral from t to b of f of x dx, provided that the limit exists. Okay, so the improper integrals, the first one of f of x dx from a to infinity, and the other one, the improper integral of f of x dx from negative infinity to b, they are called convergent if the corresponding limit exists, and they are called divergent if the corresponding limit does not exist. Okay, so the things you learned about limits in Calculus 1 will help you with these, determining whether an improper integral is convergent or divergent. Okay, part C. If both of these improper integrals are convergent, one of them is the limits are from a to infinity, and the other one has limits from negative infinity to a for the same integrand f of x. If both of those are convergent, then the improper integral of f of x dx from negative infinity to infinity is equal to the sum of the other two improper integrals. And this is true for a being any real number. Okay, so when you encounter an improper integral of this form on the left, where the limits are from negative infinity to positive infinity, then you pick a number, a, and write it as a sum of two improper integrals, and then evaluate each of those by following what was said in parts A and B. Okay, let's look at a couple of examples. So the first one, evaluate the improper integral of 1 over x dx from 1 to infinity. Okay, so I'll rewrite it. The improper integral from 1 to infinity of 1 over x dx. We'll write that as the limit as t approaches infinity of the definite integral from 1 to t of 1 over x dx. Okay, then we're going to evaluate this definite integral. T represents a finite number greater than 1. And then afterwards, we'll compute the limit by letting t go to infinity. So we focus on evaluating this definite integral. An antiderivative of 1 over x is the natural log of the absolute value of x. We're going to evaluate that from 1 to t. So this is the limit as t approaches infinity of the natural log of t. We know t is positive, so we don't really need the absolute value symbols, minus the natural log of 1. The natural log of 1 is 0, so let's just write this as the limit as t approaches infinity of the natural log of t. So what's the limit of the natural log of t as t approaches infinity? Is it equal to a finite number? So another way to ask it is does this limit exist? So you might remember from Calculus 1, if you compute a limit, and if after finding it you write that it's equal to infinity, infinity is not a number, that just tells you that it's divergent. In other words, it doesn't converge if the limit is equal to infinity. So what about this one? What do the values of the natural log of t get close to as t approaches infinity? Well, they go off to infinity. So this limit does not exist because the natural log of t goes towards infinity as t goes to infinity. So just to reiterate, this equation is written for convenience. The limit doesn't exist. I could write a complete sentence, I guess. The limit doesn't exist. So we say that the improper integral diverges. So this improper integral of 1 over x dx from 1 to infinity, this diverges. Okay, the next one, we have an improper integral of 1 over 1 plus x squared dx from negative infinity to infinity. Notice that the function in the integrand, 1 over 1 plus x squared, is defined for all real numbers. So this certainly makes sense to consider it from negative infinity to infinity. Right, there are no restricted values for 1 over 1 over 1 plus x squared. So we can write this as a sum of two other improper integrals. So how do we know what number to pick? The finite number that's between negative infinity to infinity, and writing it as two separate improper integrals. Like this is part C of the first page. Do what? Yeah, you can pick any real number. Is there one that might be nicer than the rest? Okay, I'll point out another thing. The function 1 over 1 plus x squared is an even function. So an even function is if you have f of x, if f of x is an even function, then it turns out that f of negative x equals f of x. You can see that if f of x is 1 over 1 plus x squared, then f of negative x, after simplifying, is also 1 over 1 plus x squared. What does that mean graphically if it's an even function? So the graph of y equals a function of x in the xy plane, if it's an even function, it's symmetric with respect to the y-axis. So the y-axis is like a mirror that reflects the left side to the right side and vice versa. So with that in mind, picking 0 as the value of a, so the improper integral from negative infinity to 0 of 1 over 1 plus x squared dx, and then plus the improper integral from 0 to infinity of 1 over 1 plus x squared dx. That just seems like it's going to be easier than picking another number besides 0. Let's work on this one on the right first. So the improper integral of 0 to infinity of 1 over 1 plus x squared dx. We'll write it as the limit as t approaches infinity of the definite integral from 0 to t of 1 over 1 plus x squared dx. So we've seen integrands of this type before, quite a few times, in fact. What's an antiderivative of 1 over 1 plus x squared? Inverse tangent of x is an antiderivative of 1 over 1 plus x squared. You can use a trig substitution and show that, but I'll just write down the antiderivative. The inverse tangent of x, and we're going to evaluate this from 0 to t, and then afterwards let t go to infinity. So this is the limit as t approaches infinity of the inverse tangent of t minus the inverse tangent of 0. Hey, what's the inverse tangent of 0? The angle whose tangent is 0 is 0. The tangent of 0 is 0. So the inverse tangent of 0 is 0. So now we can just focus on the limit as t approaches infinity of the inverse tangent of t. And as t approaches infinity, what does the inverse tangent of t get close to? Okay, the graph of, if t is the independent variable, whoops, this is pi over 2, this is negative pi over 2. So roughly speaking, the graph of inverse tangent of t, very roughly speaking, looks something like this. As t approaches infinity, inverse tangent of t gets close to pi over 2. So this limit is equal to pi over 2. Okay, the other half, so you'll know how to do this one now. The other half, this time we go from the improper integral from negative infinity to 0 of 1 over 1 plus x squared dx. So we write this as the limit. How am I using t again? I'll use a different letter this time. B goes to negative infinity of the definite integral from b to 0 of 1 over 1 plus x squared dx. So the limit as b goes to negative infinity, and antiderivative of 1 over 1 plus x squared is inverse tangent of x from b to 0. So the limit as b approaches negative infinity of the inverse tangent of 0 minus inverse tangent of b. Okay, the inverse tangent of 0 is 0. So we get 0 minus, and then what does inverse tangent of b get close to as b approaches negative infinity? Yeah, negative pi over 2. We have the graph up here. So as b approaches negative infinity, inverse tangent gets close to negative pi over 2. So 0 minus negative pi over 2 so pi over 2. Okay, so that means the improper integral from negative infinity to infinity of 1 over 1 plus x squared dx. That's equal to the sum of the other two improper integrals. And those turned out to be pi over 2 plus pi over 2 or pi. Okay, the next page evaluate this improper integral, the improper integral of 1 over x to the third dx from 1 to infinity. So why don't you take 40 seconds or so and compute that and tell me what you get. So is it going to converge or diverge? Okay, let's work this one out. Let's write this as the limit as t approaches infinity of the definite integral from 1 to t. I'm going to, instead of writing 1 over x to the third, I'll write x to the negative 3. The limit as t approaches infinity, an antiderivative of x to the negative 3 is x to the negative 3 plus 1 over negative 3 plus 1. We'll evaluate that from 1 to t. So the limit as t approaches infinity so this is negative 1 over 2 x to the second. Is that what you got? And then the limit as t approaches infinity. So first, negative 1 over 2t to the second, and then minus negative 1 over 2 times 1 to the second. Here we'll make this look a little nicer. We have the limit as t approaches infinity of 1 over 2t to the second plus 1/2. Okay, now compute the limit. Let t go to infinity, and what do we get? The negative 1 over 2t to the second, that goes to 0 because the denominator is getting bigger and bigger. So this term goes to 0, and 1/2 is unaffected by t. So the limit 0 plus 1/2 is 1/2. So it converges to 1/2. Okay, the next one, evaluate the improper integral of 1 over the square root of x from 1 to infinity. So let's rewrite this as the limit as t approaches infinity of the definite integral from 1 to t. For convenience, instead of writing 1 over the square root of x, what can I write? Well, convenience, because we want to find an antiderivative. So 1 over the square root of x is equivalent to x to the negative 1/2. And then we can compute an antiderivative. So use the antiderivative formula associated with the power rule. We get x to the negative 1/2 plus 1 over negative 1/2 plus 1. Evaluate this from 1 to t. Okay, this denominator, negative 1/2 plus 1, is 1/2. And if we divide by 1/2, that's equivalent to multiplying by 2. And x to the negative 1/2 plus 1 is x to the positive 1/2, which is the square root of x. But, oh yeah. Then we evaluate this from 1 to t. Okay, so we get 2 times the square root of t minus 2 times the square root of 1, or just minus 2. Now we compute the limit. So does this limit converge to a finite number? Or does it diverge? Well, as t approaches infinity, so does the square root of t. So this, informally, we say this equals infinity, but what we really mean is that the limit does not exist. So the improper integral diverges. Well, there's a little over a minute left. So we won't really get started on this one. I'll just mention a few things. I'll read this. Determine the values of p that the improper integral of 1 over x to the p dx from 1 to infinity converges by considering the 3 cases. P is less than 1, p is equal to 1, and p is greater than 1. Well, we've seen examples of all 3 cases. We did the one with p equals 1, right? The improper integral of 1 over x, that's 1 over x to the first. What happened with that one? Yeah, that one diverges. So when p equals 1, it diverges. Our most recent example was when the value of p was 1/2. That's less than 1. So what happened in that one? It diverges also. And then we had one example where p is greater than 1. That's what happened on that one. That one converged. So that's to show the 3 cases. We pretty much just go through the same process that we did in each of those other 3 examples, just more generally. Okay, we're out of time for today, so go ahead and sign in for attendance. Okay, have attendance.